A warm welcome to all the participants for this FDP session. This is organized by Department of Electronics and Computer Engineering. The FDP main aims to concentrate on embedded systems and Internet of Things hands-on experiences about the recent trends. In continuation to this FDP, we do have one more FDP planned for advances in machine learning. For this afternoon session, we have the resource person, Dr. A. Kiran Kumar. He is an associate professor from Department of ECS, KLEF. His research interests are cognitive radio and wireless communications, FBCS, and SOC design for the application development programs. And he do have the good number of research articles, numberly 34 in IEEE journals, and Kiran sir is having a H index of 7. Today he would like to share his technical knowledge for this afternoon session. I cordially inviting you, sir, for the afternoon session to associate with the participants.
Thank you, madam. Am I audible now, madam? Hello? Yeah.
Kiran sir, am I audible?
Yeah, yes, madam. Am I audible, madam? Hello? Madam?
Yes, sir. Thanking you, sir, and welcome for the session, sir.
Yeah, thank you.
Kiran sir, you're audible.
Yeah, it's okay, madam. I'm going to share my screen. Madam, I didn't get the rights.
Thanking you, sir, and welcome for the session, sir.
Yeah. Okay.
Yes,
Madam,
yes, sir.
the sharing option is not coming, madam.
Sir, you're audible, sir.
Madam, this sharing option is not coming for me. Hello?
Yes,
Madam,
sir, it is sharing, sir.
am I audible now, madam? Hello, Krishnan, madam? It's audible, madam? Hello?
But the entire screen is not yet visible, sir. Yeah. Yes, sir. Now it is visible, sir.
Okay, and my voice audible?
Yeah, you're
madam?
audible too, but volume you can increase a little, sir. It is with low volume. You're audible, but with a low volume. Somewhat, can you please increase the volumes? Yes, sir. Yes, sir. You're audible, sir.
Yeah, okay, madam. Yeah.
You're
So-
audible, sir. You're audible, sir.
Okay. The screen is also fine, madam. Yeah. So good afternoon to everyone. So today I'm going to talk about some aspects like security aspects in embedded systems and in Internet of Things. So basically in this session, mainly I will focus on some what are the security threats will be there at the hardware side. Basically, embedded system means all the connected devices. Okay, so and during this connection between these devices, we do have so many aspects in terms of security. So those aspects we are going to talk about in this session. So first of all, so as we know this in embedded security trends. So as we know, the recent studies says that most of the world's computers that will be belongs to embedded computers. It's almost 94 to 98%. And for this much of embedded computers will spread on the along the globe, and we do have security also. We have to it's a main focus to share the information or to transfer the information from one device to another device. And we do have, yeah, yeah. So with the this much of widespread of these embedded computers and embedded systems, as all the systems will be connected, and we need to take care about the main security aspects, because as we know, we are using so many the handheld devices for smartphones, and all these devices we are doing so many transactions, and we have to take care about the security aspects in these main concern. So so before that, we need to see some of the aspects. So the first one is like software and hardware complexity. So as we know, recent trend, we are using these most powerful microprocessor or microcontrollers. So we have so much complexity. Means so each and every the controller or processor, it is 64-bit, and it is so complex, and it takes more power. And so these things also we need to take care. And next one is the processor consolidation. So whatever the processor we are going to choose for this or any kind of the application, first we need to select the processor and what is the kind of architecture it has, and how the transactions, means the data transfer between one processor to other devices, like maybe memory or any IO devices. So that we need to take care. Okay, because at that point only we need to get the threats from the attackers. So the next one is network connectivity. So as we know, all the nowadays all the devices are connected to the internet. So maybe LAN or WAN. Okay. So these connectivity between the device to device. Okay. So at that point also we need to take care about the security, because in between maybe some attackers may come. They can spoof the data. They can grab all the main information like passwords and this. They can grab, and they can steal all those things. So in this aspect also we need to take care about the security in between, connectivity between the devices. And coming to the software side also, we have so many malicious softwares, Trojans. Okay, these things will have the threat to continue in this embedded system growth. Okay, as the complexity is increasing at the same time, so we are getting so many so many flexibilities in designing the systems. In the same way as the complexity is growing, and the security also we need to make it strong. Otherwise, no, because the attackers, not only for the software side, hardware side also, the attackers can attack the system and they can malfunction, or so they can grab the main important information. Okay, so in this aspect, we are going to see, I'm giving one of the example here. So this is a smart grid application. Okay, so it is also, it comes under embedded systems and IoT. So as we know, smart grid. So each and every home not only consume the power, they can generate the power by using wind power or solar power. Okay, so these so after consuming the power in our houses, so if the remaining power, they can be uh, give it to the some other like substations or grids. Okay, so this is what the smart grid. So here, so each and every home having some smart meters. Okay, and the smart appliances like refrigerator, AC, all these are smart appliances we have. So these appliances will use one gateway. So they will send the information how much the power they are consuming, and what is the remaining power that they have. So that information will goes to the near neighborhood gateway or aggregator, you can say. So like these all homes. So whatever the information they have regarding this power, so that will be transmitted to the gateway, and from the gateway to the substation, and from the substation to the grid operation center. So in this way, it is, you can see, so it is totally connected in a network. Okay, from the small home to gateway, and from the gateway to substation. Substation will connect most of the neighborhood, all the gateways to the substation. Then all the some of the substation will be connected to the main grid. So this is what the network we have. So the securities here, they have the major role here. We need to check it. Otherwise, no. You can see in the smart home itself, what we are sending, coming to the bill, what we are paying, what we are generating, and what we are consuming for that. So if something happens, no, so what are the bill that we are paying, no, that we can do some malfunction. So maybe the attacks between the network connectivity, or maybe some threads in the system, maybe your smartphone or smart appliances. So that we can do. So that is what the hardware perspective we have to see. This how the attackers they can attack on these systems. And as we know, the complexity. So nowadays we are having all the embedded systems which are more complex. Okay, and from the lowest to automobile contains that contains dozens of controller or processor, and might be running on either Windows or Linux OS with the millions of code. Okay, so this much of complexity, as it is increasing linearly coming in the hardware and software side, so it creates more than the linear growth in overall complexity due to this exponential increase interactions between the functions and your component inside your system. So this, as the complexity is increasing, so it breeds the flaws. Okay, so there may be security breaches will be appear, and these flaws can be exploited to breach your system security. So as the complexity increasing, it is trying to give some flaws. Okay, so these flaws, they will be used by the attackers, and they can attack the system. They can malfunction, or whatever the data you are sending from your device, that we can change. Okay, so all these things can be happen in your systems. So yeah, so this is the aspects that we can see from the security aspect. So now I'm going to show you, as we are using so many ICs, hardware integrated circuits that we are using in our embedded systems. So how during the hardware development or either software development, we have these attacks. Okay, so now in the next slide, I am going to show you how that IC what we are using in our embedded system. Okay, so what is the flow, how they are designing. Okay, and in the during this design also, from manufacturing, from that design to after the last step of your manufacturing the IC. So in between these stages also, we do have the attackers. Okay, so that we are going to see how the attackers will attack, and how we can countermeasure that, how we can avoid those attacks. So these things we are going to discuss a little bit. So this is the flow of your any hardware IC that they are going to design by all the manufacturers. So first, the step, design integration. So first we will get the specifications from the customer. So according to the customer, the uh, design will be started by your design teams, and in the design team, so we do have, uh, suppose if you take any company, so in-house designers will be there, developers. So they are going to design some of the blocks of your system. So whatever the customer they require, and some of the blocks maybe they can buy from the IP vendors. Okay, so for example, we have some IPs like some Eric Saber's IP, or these IPs we can't design in the design team. So automatically, for example, in the Xilinx, we do have like those IPs, intellectual properties, so that we are going to take directly. Okay, and some other third party IPs also will be available. They are going to buy by the company, and they are going to integrate in your design. So after all these things, so we do have the developers in our team, and also we are going to get some of the blocks from the third party. So all these things will be integrated, and finally you are going to get we are going to develop your the final application. Okay, so after that, then we are going for RTL netlist. Okay, so all these things maybe you can write in either Verilog or VHDL according to your spec requirements. Then finally, you are going to generate the RTL netlist. Okay. Then we do the verification. Okay. So we will verify all the netlist, and so whatever the outputs or the requirements it is meeting or not, that we are going to see. If it is not meet, again you have to go back for design integration. You have to check that errors, if some errors will arise. again you have to generate the netlist according to that. Then you have to verify if it is everything is okay, then we have to go for synthesis. So synthesis is nothing but what are the code you are writing that you have converting into logic gates. Then gate level netlist. So all the in terms of gate level netlist you will get it from that. Then physical synthesis. Okay. So this is all a backend physical synthesis. Then finally you will get layout of your that IC. Okay. Then after getting the layout, again we do verification. So finally you will get this GDS2 file. So that is the main file for after all the synthesis and verification of your IC, you will get that file. And after that you have to go for fabrication. So after you are getting that GDS2 file, that you have to give it to some third party foundries. Okay. So these foundries, they are going to manufacture your IC physically. Okay. So, and then the foundry also, they have the chances they can insert some virus, or I can say Trojans or some hardware malfunctions. It may be chances will be there. Okay. So this foundry will get the GDS2 file, and by using all the techniques like wafer, and finally they are going to get your IC. Then after that we have the testing team. So whether that IC is meeting our requirements or not. So all the specification, okay, timing and power consumption. So everything it is meeting or not. So if something goes wrong, again we have to go back. So here after that finally you have to package your assembly. Okay. So then after packing and assembly, finally you are going to get your hardware IC. Okay. So this IC again you may use in different applications. Okay. Like you may use in PCB assembly or in some other applications, or you are combining this IC along with some other ICs to make one system. So this what is your system integration. So this is the flow of your total entire one IC design flow. So design, after that synthesis and verification. Okay, if everything is fine, then we will go for fabrication. In after fabrication, we have to go for testing, then packing that IC. After that, that IC you may use in any one of the application, or you have to assemble in one of the system PCB. Then you can go ahead with your application. So this is the flow. So in these steps, so we do have so many attacks. Okay, first step is design. So in the design, some group will be there. Some of the developers or some other IP vendors. So they may introduce some of the virus like Trojan. So that may be in the form of your the gates. Okay, and in the next level, the verification, synthesis and verification. So if the tool is having some any malfunction, then you may got that errors. And in the fabrication, so that these are the third party vendors. Okay, so these third party people, they may have they may add some more extra circuit, so that will be acts like a virus, or you can say Trojan. Okay. So and also testing, in testing also you have to check whether all the whatever the user requirements it is meeting or not, or it is sending some false information to some other block. So these things everything we have to check it in the testing section. So if any one of the level, if you are going something wrong, then finally, so we do have so many attackers we have. So so with those things, you can the information might be stolen. Okay, and or it may be in some critical application. Suppose this IC I am using some missile application. So in somebody in this flow, they have introduced some Trojan. Okay, so that Trojan will be activated during some instant. Okay, that they may be controlled. Okay, so, so if something goes wrong in your direction of your missile, it may be have to bomb in Pakistan, but it might be go somewhere. So this kind of this we can that kind of attacks also will be there. So we have to avoid these attacks, and we need to secure our the flow also even. Okay, from the starting specs to final manufacturing your IC. So we need to take care of all these security aspects in this flow. So how we do have those things? Let's see. So what are the threats we have? First one is the Trojan, hardware Trojan. So an attacker in your either design house, so during the developing your hardware, or maybe in the foundry, they may add some malicious circuit, or they can modify the existing circuit. It is also something kind of Trojan, or modify the existing system, or they can add some more extra circuit, okay, to malfunction your the operation of your IC. And another attack may be like IP piracy and IC overbuilding. So IP piracy, so you are getting some IPs from third party vendors, okay. So this IP may include something malicious things in their IP, and the same IP we are using in our application, then that makes, okay. So this IP user or a rogue foundry may illegally pirate the IP, okay, and without the knowledge and consent of the designer. So this foundry people also, without consenting uh, the customer, they can add something, okay, they can add some extra circuit or they can remove something. So if something happens, no, that's, so it costs more, okay. And also some people will do IC overbuilding. Actually the customer will ask only 1000 ICs you need to manufacture, but the foundry people, they will overbuild, means instead of 1000 ICs they will manufacture some 10,000 ICs. So the remaining ICs will goes to the black market. So this also will happen. And the next one is reverse engineering. So we will talk about clearly in the next slide. So, and one more attack is side channel analysis. So in this side channel analysis, so the attacker can extract the secret information, okay, from your IC uh, without physically attacking your IC. You can grab the information what is happening inside your IC. Okay, so that may be by observing the power consumption of your IC, and what is the timing of your IC, and what is the radiation, so EM radiation. So with these things also we can analyze what is happening inside your IC. So suppose you can see some of the ICs that are executing some like cryptographic algorithms, or they are taking some inputs like keys. Okay, those are very important. So with the help of this analysis, no, you can grab that the passwords or the keys, and also you know that what kind of algorithm they are running. Okay, if you know that algorithm, you can easily crack that codes. Okay, so these things can be you can attack by using this method, side channel analysis. So by observing the power consumption of your IC, and what is the timing, and what is the electromagnetic radiation. So with the help of these things also, you can analyze what is going on inside your IC. Okay, what algorithm you are running, so what are the keys that you are going to take, everything that you can monitor. Yeah. So these are the attacks we have: hardware trojans, IP piracy, and IC overbuilding. So reverse engineering, I'm going to explain in the next slide. And the next one is side channels and the counterfeit ICs. So these are the attacks we do have, and to avoid those attacks, we do have some of the countermeasure techniques. And every countermeasure technique would have some security metric, means each and every countermeasure technique, so in up to what level they are going to secure your hardware. Okay, so one of the countermeasure is like design obfuscation. So obfuscation means we are just confusing the design. So by looking, it looks like, suppose it is a NAND gate, so it looks like NAND gate, but the functionality is different. So that is what the obfuscation, we are confusing that attacker whether it is an AND gate or not. Okay, that is the technique we can implement in designing the hardware. And IP watermarking, you know that. So IP fingerprinting, IC metering, and split manufacturing. This is also important one. So normally any customer will give whole IC design to one of the fabricator, then it uh, we do have the chances they might add something extra circuit, or they can remove something. So to avoid that, some people will do split manufacturing. Split means some part of the IC will be built by one foundry, and some other part of the things will be manufactured by the another foundry, so that they are dividing that the blocks of your IC. Okay, so they are splitting the manufacturing of your IC. Then IC camouflaging. So this is also like that. Camouflaging means it looks like something, but it will execute, or it will give some operations different. And in the same way, we do have so many attacks. And finally, you can see here uh, PUF, physical unclonable function. So physically unclonable function. Physically you can't see that function. Okay. So like that function we can use to generate any keys, security keys or passwords. Okay. So there we can use these countermeasure technique to avoid these attacks. And also we having in the last column security metrics, the number of attempts to find the secret. So how many attempts you are going to take to get any the password or something keys. Okay, so how many attempts you are going to uh, doing to get the exact keys. So and the number of collisions, amount of information leakage, probability of detection. Okay? So these are all metrics uh, to measure how much these countermeasure techniques are working. Okay. So yeah, actually I skipped the reverse engineering. What do you mean reverse engineering? So this reverse engineering is a very powerful technique, and yeah. So this reverse engineering of an IC is a process of identifying the its structure. Structure means inside. Okay, and what is the design and what is the functionality it is doing. Okay, so nothing but you are physically damaging your IC, you are opening your IC, and you are looking what is the structure of your IC and what is the design that you are performing in your IC and what is the functionality, everything that you can grab from your IC directly. So that's what the reverse engineering. So here, so why we are using this reverse engineering? So why we are using this to collect the competitive intelligence? Actually, in some countries, this reverse engineering is also legal, not illegal. Okay, so legal means they can prove that. So my IC and my manufacturing of your IC, it is very hard to get your logic. Okay, so that is also one of the metric actually. So we do have some companies in other countries. So this reverse engineering makes that so okay, my IC is more strong to any attacks that you can say. So that's what the to collect the competitive intelligence and to verify a design and to check for any commercial piracy. Suppose one of the manufacturer they have not paid anything to that IP vendors, but they are using that IP. Okay, so this reverse engineering, you know that. So this IP it is not so he did not take any rights to use that IP, but even though he is included that IP in his IC, so that is it is illegal, right? So these things we do know by doing this reverse engineering, and also patent infringement. If somebody some of the blocks maybe they have to patents, so without consulting them, they can use that the logic or the design in their ICs. So all these things we can check by doing this reverse engineering. Okay, so how what is the flow of this reverse engineering? How they will do? So so in order to do this process or this reverse engineering, first the attacker what he will do is first he will get that IC from the market. Okay, it may be a dip package or BJ package, whatever the package. So he's going to get that IC from market. And first step is so what he will do is he will depack that IC. So the plastic package will be there. So that he will remove that. So by using some corrosive chemicals. So after that, what he will do, he will delayer each and every layers. So nowadays, each and every IC having 3, 4 layers will be there. So he has to delayer that all the layers like metal, poly, or diffusion. So by using the chemicals, some corrosive chemicals. So after that, finally, he is going to see that structure of that IC. Okay, the design structure. So it is in the form of all the transistors. Now that structure is going to take the image to all the views, so top view, bottom view, okay, all views. Is going to capture that image by using some powerful microscopes. Example SEM, single electron microscopes. So these are very powerful. So with the help of these devices, we are going to grab all the images of that IC. Then what the next step is, we have to annotate it, aligns and stitches the image of the different layers. Suppose we are having 3 layers. So each and every layer, I got the image. After that, I have to stitch it all the images and the connections what they have. So they have to annotate it and they have to align the layer, each and every layer. So after that, you have to annotate it means you have to say this block or this portion of that image is some, this is an multiplexer. So this is an decoder. So they have to annotate it. And after that, finally, so after doing all these things, you know that this part is something like bigger level. This is an ALU, and this is something else, and this is a decoder. So this is a modulation things. So all these blocks of your IC, they are going to get that. Then finally, if you know all the gates and the blocks, so finally you can get the gate level netlist from that annotated images. And this, it is a legal because we do have some softwares like chipworks and dgate. So by with the help of these softwares, so if you have the image, finally you will get that gate level netlist. If you have the netlist now, everything is done. You can give the netlist to some other manufacturer and you can produce whatever you want. Okay. So with the help of these softwares, you can extract the gate level netlist from the images. And finally, if you know that netlist means extraction of, you can do the functional specification also. Okay. After getting the netlist, you can perform the what is the function it is doing. So everything you know, you do know. Okay. So these are the steps that we are following in this reverse engineering process. So as I said, this reverse engineering process is illegal in some countries. Okay. So because they know, so what are the things they are including? Okay, maybe some third-party IPs or their designs, everything they don't know that. And not only for legal, it's also illegal because some other companies. So suppose Philips is manufacturing some IC. So some other attackers, what he will do? He will do the reverse engineering. So to manufacture IC, we do have so many steps. Okay, design team is there, verification, synthesis, after that foundry, okay, backend, physical verification, all the things you need to do. And it is billions of dollars they have to spend by the manufacturer. Okay, but without this, okay, and you have to spend 1 or 2 years to manufacture each and every IC. Okay, and they are with the help of this reversing, they were avoiding all these things and then just they are getting one IC, they are doing reverse engineering, finally they are getting the specs, means what is the functional specification of your that IC. Okay, so without all these flow of these steps, so by doing this reverse engineering, they are going to grab the design and they will do the manufacturing by giving that netlist to some other foundries. Okay, so this reverse engineering is also one of the attack, and we do have some techniques to avoid uh, this reverse engineering. So we are going to see that. Yeah. So how thwart the this reverse engineering? So how we can avoid this reverse engineering? So what are the techniques we have, and how we can do that? Okay. So everything we are going to see here now. The first technique is logic obfuscation. So obfuscation means just confusion. So the logic we are going to confuse that. Okay. And now, so what happens here it is. So it hides the functionality and the implementation of a design by inserting some extra circuit or extra states in a state machine. Okay, so for example, like I have designed one full adder. Okay, so normally, generally, assume that the full adder consists of only four states. But what he will do is he will add some more extra circuits or extra gates he is going to add. Okay, but for the functionality, it is like full adder. But going to see the design, so it just obfuscate that design. But finally, the operation of that original design and this obfuscated design both will be same. But for looking, it will be different. And the next one is IC camouflaging. So complementary technique to your logic obfuscation. So logic obfuscation, here you are going to introduce some extra gates. Okay, or in your Verilog or HDL design, you are going to add some extra state machine or extra some logic you are going to add. But wherever in IC camouflaging, so you are going to obfuscate or confuse that attacker. You have to add at the physical level something. Okay, IC camouflaging. So what we will do in this IC camouflaging, it operates at the layout level, not at the logic level or your Verilog or PHL level. So at the layout level, we are going to introduce some techniques. Okay, so that may operate at the gate level or RTL level. Okay, so we do have some techniques. So I'm going to explain that also. So what do you mean this IC camouflage? So it is going to avoid your reverse engineering. So the attacker should not be able to identify the functionality or what is it is doing that the design what they are going to attack on that. Okay, so the functionality of a camouflage gate, and then layout also, the layout of the logic gates are designed to look identical, but the resulting in different operation or different functionality it will do. Okay, so for example here this is one structure layout level. So here you can see we have three functions: NAND, NOR, and hexa. And here you can see, so for each and every transistor to connect, we need some contacts, poly layers. Okay, so here we have some contacts that are, some contacts are true and some contacts are dummy. Okay, but for looking, okay, if you are seeing by eyes, it looks like NAND gate, but the operation of that NAND gate is not NAND gate. So the operation is NOR gate. So to do that, what we will do is we will add some extra contacts, so that are called dummy contacts. Okay, but for looking, it look like a contact, but physically it is not. Okay, so like here in this example, so there is a NAND gate. So you can see the number of contacts here. We number 2, 4, 6, 8, 11, 12, 16, 17. These are the two contacts. But we do have the, again the same way dummy contacts also there. Okay, so these dummy contacts actually physically they have not connected, but for looking, okay, for observing that structure, it looks like a contact, but it is not. So in this way, we are going to confuse or we are going to obfuscate our IC. Okay. So what are the capabilities of an attacker? So suppose the attacker have the knowledge of that logic functions and the routing of the all non-obfuscated components on the circuit from imaging layers of the delayered chip. So if he has the knowledge of these logic functions and the routing and what are the contacts exactly what it is, so he, in that case he might be attacked, and so that may be leak. I mean they are going to get the exact circuit. Okay, and the attacker has a knowledge of which components of camouflage and knows the possible functions they can implement. Okay, so from that images, as camouflage components look different from other counterparts. See, if you are adding something extra means it will look like something different. So that knowledge, if he has the attacker, we are gone. Okay, so that we need to take it. Okay, so it should not be like entirely different circuit from the original circuit. So what are these camouflage components? We do have some camouflage standard cells with the dummy contacts, and another technique is obfuscates and transformable interconnects. So the first one is camouflage standard cells with dummy contacts. So here you can see. So here I'm giving one multiplexer here, and this multiplexer is 3 by 1. So here I'm having three kind of inputs. One is NOR gate, NAND gate, and XOR gate. So by giving this programmable that mux PI and PI plus 1. So by giving these select lines, it is going to take that one of the input, and that will be given to the output Y. Okay. So with the help of this standard cells with the dummy contacts. Okay. So here you are going to give AB. Okay. So AB means you don't know whether this your mux is performing NAND gate or NOR gate or XOR gate, you don't know. But by giving this the two inputs PI and PI plus 1, okay, and these are not visible to them. Okay, only the visibility is only A, B. Okay, so you don't know whether this block is functioning NAND gate, NOR gate, or XOR gate. But if you do know that PI plus 1, if it is 0, 0, NOR gate will work. 0, 1 means NAND. Okay, 1, 0 is XOR gate. So these programmable inputs are not visible. Okay, so with the help of this, it's going to confuse. Okay, this block is either NAND gate or NOR gate or XOR. He don't know. Okay, and you can see another this. This is what the fully camouflaged. So here also having the 4 inputs for this mux and 2 select lines. So by giving these inputs, they don't know. I mean, this function is whether it is NAND gate or NOR gate or XOR gate. So in this way, we are going to camouflage your IC and the obfuscates. So here also, for example, the dopant programmable logic cells. And as you know, so we do have some for NPN, PNP transistor, we do have some considerations of the dopant. So as the operation of the NPN transistor, if you do some changes in your concentration dopant, it is going to act like some other transistor like PNP. So those dopants also we can program that. Okay, so that we can do by using this obfuscates. So obfuscate, see, this obfuscate will consist of again obfus cell. So obfus cell is nothing but 1 mux. Okay, so it is 4 by 1 mux. So PI and PI plus 1 are, these are the two programmable inputs. Okay, so you have the 4 inputs. One is direct, another one is inverted, another one is standard 1, and another one is standard 0. So with the help of these 2 inputs, you are going to get whether whatever the input is coming to your upper scale that need to go directly, or whether it is complemented, or directly it is 1, or directly it is 0. So these things will be done by the help of these dopant programmable inputs. So and then interconnection. So here you can see one circuit diagram over here. So in the middle of the wires, we connected a small mux, 2 by 1 mux. Okay, so with the help of these select lines P0 and P1, okay, and these contacts, see here, this technique, they are using 2 types of interconnects. First one is magnesium contact, and which is conductor, and next one is magnesium oxide, so that is non-conductor. It's like an insulator. So you don't know whether the contact is connected or not. Okay, so with the help of your images, by doing the reverse engineering, you will get the image, but you don't know whether it is this contact is made with magnesium or magnesium oxide. You don't know. So in this way, you are going to confuse that attacker, so whether this contact is there or not. If the contact is made with magnesium oxide, it is actually open, means it is insulator. No, it is open. There is no connection. But the attacker, what he will think, say it's a connection, so that he will grab all the images and he will consider it's a mark something kind of thing. So that in this way, they are going to get all the functional verification. But finally, it is wrong. So this is the what we can avoid this IC using this IC camouflaging technique. We can avoid this reverse engineering process. And the next one is Trojans. What is this Trojan? Trojans are nothing but a virus, but so here we are talking about in terms of hardware. Okay, so here these Trojans are, the nature is like a stealthy, means what are the information in your hardware system. So those things they are going to steal. And one more thing is it is very difficult to create that Trojan model. And these Trojans you can insert at any phase of your IC design flow. So during the design integration or IPs, okay, we are going to integrate some third-party IPs. They may also include these Trojans, or in the time of fabrication. Okay, so the fabrication people also they might have add some extra circuit, or they may remove some of the gates from your logic. Okay, so these things will be happen, and the nature of this will be like a stealthy and very difficult to create the model, and you can insert any phase in your IC design flow. So what is the impact that you can get from by inserting these Trojans. So what they will do is they will change the functionality of your design. So that's what we are intending to do that. And they can leak the sensitive information like the keys, okay, crypto keys or passwords, and you can experience the degraded or unreliable performance. Okay, so if you are getting all these things, you are changing the functionality of a design, and it is leaking that main information like passwords. Okay, so it experiences or degraded of your performance of your ICs. What it contains exactly? What is Trojan? So Trojan is nothing but it is also a circuit. Okay, normally it contains a payload. Payload means uh, your the Trojan circuit, and the next part is trigger. Okay, so normally what are the operation that the customer requires? So in normal mode, it is going to act like the same IC whatever the customer needs. Okay, but at some point of time, okay, so this trigger might be going to trigger, okay, at some point of instant. So normally basically what it will is this trigger thing will monitor all the signals and the events what is happening in your circuit and may utilize the don't case states. So in the case statement we have so many case statements we have. Yeah, yeah, sorry. Yeah, so these Trojans, it contains mainly the two parts. First one is triggering part, and the next one is payload part. So normally this trigger part, what it will do is it monitors all the signals what it is going inside your IC, and it is going to see the events what is happening when some parts of your blocks are going to active or when it is deactive. Everything will be monitored by this trigger circuit. And normally, in the case statement, we do have some laws. The default case will be there in your software. So that don't care conditions or the don't care states, they are going to take that states. So with the help of that states, they are going to see so what is happening in your IC. Okay, what things that you are going to do. And whenever you get that trigger, what it will do is it gets the input from the original circuit. So what is happening in your original circuit, that they are going to grab that and they will trigger this payload. So payload will be activated, and what it will do is this payload going to malfunction your IC performance. Okay, suppose it is doing addition operation. By triggering this, instead of addition operation, it will do some subtraction. So in this way, they are going to trigger this circuit. Okay, so in this is what the one example of your Trojan. So when this payload is inactive means your IC, it acts like a normal circuit. But whenever it is going to trigger that at that instant, and so whatever you expected that operation will not come. Okay, some what it is going to do is it is going to maybe extract your keys or it is going to malfunction your functionality of your IC. So all these things will be done whenever you do the triggering of this payload, and this triggering will be done by whenever some of the events may occur, or for example in don't case states. So in this situation, they are going to trigger that payload. Okay. So what are the countermeasures? So this is the attack. So how we can avoid these Trojans? So we do have some countermeasures. First one is detection, then design for trust, and then split manufacturing for trust. The first one is detection. So first, instead of uh, to countermeasure this attack, first we need to verify our design is perfect or not. So without any Trojan or without any extra circuit or without less number of gates for what we intended. So all these things we have to detect it first. So verify the existing design and so whatever the GDS2 file that will be given by the customer to one of the fab lab. Okay. So before that giving what is the circuit and after the manufacture of your IC, what is the circuit? If the both circuits are same or not. So each and everything you need to check. So what is the functionality? Is it true? Is it okay or not? Then the power consumption and the timing, everything you need to check. So with this analysis, you might have detect if any something is added or any Trojan is there or not. Okay. And the next technique, design for trust. So plan for the Trojan problems in the design phase through the design for trust. It facilitates the detection approaches. So, so main thing is the main chances will be there in your design team itself. So you have to trust your design team. So to avoid any extra circuit or any uh, extra circuit or you're going to remove some of the parts of your IC. Okay? Even though your circuit is working fine, but at some instant, that's what the triggering you don't know. So whenever that will do trigger or it will activate your payload, that only the designer know. Okay, at what point of instant that is going to activate. So before that, we need to trust our design team and to avoid all these things. And then already I told you the split manufacturing trust. So use the state of the art semiconductor foundries, and you have to split your the flow of your IC. And as just now I said, some part of the blocks of your IC will be manufactured by some foundry, and some other blocks will be manufactured by some other foundry. In this way, you are splitting so that they don't know exactly what is happening in that IC. So in this way, we can avoid these Trojans. So in the detection, again, we have before and after of your IC manufacturing. So pre-silicon, post-silicon. So pre-silicon means before going to your foundry. Okay, so everything is in software. So that's what the pre-silicon. So post-silicon means after manufacturing. Okay, after getting your hardware IC. Okay, then how you can detect that Trojan. So pre-silicon. So pre-silicon means first we do have so many verifications are there and testing is there. Everything uh, you need to take care about and you have to validate the course what you are using in your design. First one is functional validation. So it should be effective. If any Trojan is inserted by the design team, means you need to detect that first of all. Okay, so all the verification it should be done. 100% coverage you need to take care, and it cannot help. Suppose in some situations, it can't help in cases where the Trojan may transmit some information or modify the specs. Okay, so it is also one of the drawback here. And the next one is code structure analysis. You need to identify all the states. If any don't care states are there, that you need to take care what is happening in that state. Okay, and finally, formal verification. If you are using any algorithmic based approach for the logic verification, so you have to exhaustively approve that predefined set of security properties that your design is satisfying or not. And your drawback is in this verification is it can fail to detect any unexpected functionality introduced by your Trojans. But what are the conditions that you need to verify in your formal verification that it will go through? But in some cases, okay, you might have the chances that the Trojan will uh, it can it can detect or it can do some unexpected functionality. Okay? So that if you are skipping that kind of thing, no, your this formal verification will be there's no use in this to detect any Trojans. Then post silicon. So post silicon means after getting your IC. So post silicon means we do have again two separate techniques. First of all, destructive, non-destructive. So destructive means you have to open that IC. So non-destructive means without damaging your IC, you need to check whether my IC is perfect or not. Somebody added something, this Trojan or not, that you need to check. So destructive means you have to depack that, whatever we are doing that reverse engineering, okay, the same thing. So you have to depack that IC and get the images by using some powerful microscope and construct your final gate level netlist. Okay, so here you can see, so with the help of this, you can check whether any unexpected Trojan is there or not. Okay, but it is very high cost. Okay, you have to use some powerful microscopes and you have to use some software. So it is very high cost, and it might take several months or weeks. And these ICs you can't use after open this IC. Okay, physically you are opening that IC, then you can't use that IC for further use. Okay, it is not you can't use that. And the next technique is non-destructive. So we are not going to harm your IC. Okay, simply get your IC and we will do some functional test. Okay, it can be effective if the Trojan changes the any functionality of your circuit, but in some cases it can't help. The way Trojan may transmit some information to with an antenna or modify the specs. Okay, and the next technique is side channel analysis. So just now already I told you. So side channel analysis means after getting your IC, so you need to monitor so how the power is consuming. Okay, how the power is consuming and what is the delays and timing diagrams. Okay, voltage and current, how it is varying, and the radiation also. So by observing all these things, you can expect what is happening inside your IC. And in crypto, some crypto algorithms they are running. Suppose uh, see the they can see the analysis of your with these parameters. They are going to get exactly what kind of algorithm they are using. If you know that algorithm, it is easy to find that keys even. Okay, so these are what the countermeasures in detection. Then design for trust. So here you have to facilitate your design. Okay, your design team you have to facilitate how you can detect the Trojans, and you have to make sure that the verification is 100% or not. And the next one is preventing the Trojan insertion. So you have attempts might be to you can avoid this hardware Trojan insertion by attackers. And the last one is trustworthy computing on untrusted components. So Trojan detection and recovery at these runtime means your the computing watch whatever you are doing in your IC, you have to do with the uh, you have to do with untrusted components. So these are the countermeasures that we can do under design for trust. And the last one is split manufacturing. Already I told you you have to divide your design. So there are two things like front end of line and the back end of line. Okay, the front end of line is it costs higher, but in you have to untrusted foundry you have to go for, and the back end of line it is a lower cost, but you have to be manufacturing the trusted foundry. So where we have some nowadays we are getting 3D IC, 2.5D ICs. Okay, so 2.5D ICs these chips fabricated in untrusted foundries, and some other blocks like interposer they are manufactured in a trusted foundry. And the 3D ICs coming to this, these chips are fabricated in untrusted foundry and TSVs. Okay, through silicon views connections. These connections will be done in your trusted foundry. So in this way, they are going to split your the manufacture so that the attacker don't know what is exactly the design. Okay, so that he can't insert the Trojans perfect. Okay, so till now we discussed about what are the aspects in this security aspects of security for embedded and hardware designs, and these application you can use in your real systems and Internet of Things applications. And next we discuss some uh, we discussed on the reverse engineering how we can do that and what are the things and what are the countermeasure techniques we do have to avoid the reverse engineering, and also Trojans. So Trojan means nothing but a virus that they are adding in your hardware. not in the software. So what kind of Trojan will be there? What are the blocks inside your Trojan? How you can avoid that? Some countermeasure techniques like detection, design for trust, and the split manufacturing. So these are the countermeasure techniques that we saw right now. So next one is we are going to see one technique. So that is what the PUF, physically unclonable function. So it is quite interesting. So what we will do in this is, so physically unclonable function. So physically you can't clone that function. Okay. See, that means suppose you do have one IC. So each and every IC having some different architecture and some delays will be there different. Okay. And the power on state of your RAM memories and the threshold voltages and many other physical characteristics to derive this secret. Okay. Suppose, for example, you got two ICs of the same manufacturer. Okay. Of the same manufacturer, suppose Atmel IC, two ICs I got. Now you can say whether these two ICs are both are exactly same. No. Why? Because so due to this manufacturing process variations, you can't say that these two ICs will perform the same way. Means maybe the delay might be a little bit different will be there. The power consumption also might be a little bit different will be there. Okay. And the threshold voltages of your transistors might be different will be there. Okay. So these are all parameters are unique to each and every IC. Okay. So that's why, so these parameters I'm going to grab it. So it acts like an ID. Okay. So it acts like an ID. So for each and every IC having their own IDs. Okay. So we have some primary applications of this POPSOR. We are using in the authentication purpose and also secure key generations. So what are the advantage of this POP? So it requires very simple and easy digital circuits we have to use, and it is very low power and very less area you need, and now invasive attacks are more difficult to execute without modifying the physical characteristics. Suppose you are getting one IC and you are doing some reverse engineering. So with the reverse engineering, you did not get exactly what are the physical characteristics. Like by seeing the image, you can't say what is the delay it has, how much power it will consume this block. You can't say that. Okay. So continually, it is powered active anti-temper mechanisms that are not required. Okay. So here, so by implementing these PUF, physically unclonable functions in your ICs, so it acts like an one ID to your IC, so that you can see previous some attacks IC overbuilding, IP piracy. So these things you can't do. Okay, you can avoid from by using these puffs. Okay. Yeah. For example, we do have so many different kinds of puffs are available. So here I'm taking one of the simple example here, RO puff. RO means ring oscillator. So for example, now this RO puff is going to introduce in each and every IC. Okay. Now again the same example I took two Atmel ICs, maybe 8-bit microcontroller or something. So these two ICs are different. Okay. So how I am making difference is that ID. So inside your microcontroller, you do have so many gates will be there. For example, you are taking one FPGA, you may have so many gates will be there, NAND gate, NOR gate, all these things. So what I will do is I'm going to construct one ring oscillator. So yeah, nothing but a ring oscillator is a combination of some of the NAND and NOT gates. Okay, you can see here. You can see one example here. So a series of odd number of NOT gates. Okay. So first NAND gate is it is going to enable that. Then what it will do is after enabling this, what will happen is you're going to take a feedback of here. See. Then what it will generate is it is going to oscillate in between 0 and 1 each and every time. So this, it might be 3 NOT gates or 5 NOT gates or 7 NOT gates. Like this, so each and every this RO block going to generate one signal. Okay. So this is an oscillator signal. So each and every oscillator signal may have one frequency will be there. Suppose, for example, this frequency is suppose 1 megahertz, for example, and one more oscillator block is there. So it is also have connected 5 NOT gates, so that it is generating some oscillator signal, might be 2 megahertz. Like that, uh, I'm constructing more number of oscillators. Suppose 10 oscillators are there, 10 signals are coming. So each and every oscillator do have their unique frequency. Okay. So all these frequency signals I'm giving to one mux. Okay. So here the two muxes I am using over here. Okay. So all the ring oscillators I am giving to these two muxes. Okay. And one of the signal I am going to select by using this select line. That's what the input here. Okay. So by giving some 00 or 10, it is going to select one of the RO oscillator signal. So that signal is going to one counter. It acts like a clock. Okay. Then the counter will start and it is doing counting. So it may be 8-bit counter or 16-bit counter. It keep on continuing the counting 1, 2, 3, 4, 5, 6. Okay. So at some instant, what I will do is I just compare these counters. Okay. So because these uh, signals, okay, from each RO you are getting different frequency signal. So one is 1 mega, 1.2, 1.3, 2 mega or 10 mega. Okay. Then the counter speed also will be changed, right? But at some instant what I will do is I will compare the two counter outputs, so that suppose counter 1 is greater than and this counter 2, then I will get 1, otherwise it is 0. So in this way randomly I will get zeros and ones. Okay. And this structure is unique to each and every IC. Okay. It won't be same to all, because as you know the process variations will be different. So this NOT gate, the NOT gate delay here it is suppose 1 nanosecond. Then some other IC it might be 0.9 nanosecond or 1.1 nanosecond, but exactly it won't be there. So the same that parameters I'm grabbing, okay, with the help of those things I'm going to construct one oscillators. So I'm generating the signal, I'm giving 2 mux, and that signal is going as a clock to one counter. It is going to count the numbers 1, 2, 3, 4. At some instant I'm going to compare these two counters. If it is greater I will get 1, otherwise it is 0. Okay. So this structure, by looking okay, this is RO block, I know, but you don't know what is the frequency it will get. Okay. So in order to get the frequency also you need to all the process variations. You should know what is the threshold of that transistor, what is the delay of that each and every gate. So if these things then only you will get your the frequency of the signal. Okay. So it is very quite difficult. So that's why we are saying it is an physically you can't clone the function what it is doing. Okay. So we have some characteristics of this puff, whether this puff is strong or weak. So the strong or weak that we are going to decide uh, by by checking some parameters like uniqueness. So what is the uniqueness that you are getting from the uh, output of this puff? So for this puff, input we will call as a challenge, output we will call as a response. So this is the pair. For this input, what is the output? Input means the select pins, select inputs, and the output is the comparator output is your response. Okay. So these are the pairs, challenge and response. So here RI and RJ, these are the response outputs from the ith and jth device. I took two devices. I have given the same input, but your responses will be different, right? It should it will come. So you are taking like the some L number of devices and you're giving the same challenge, but the responses will be different. So that's for the uniqueness. So ideally it should be 50%. and reliability. So how much I can reliable on this puff? So based on the distance, having distance, I'm going to calculate each and every challenge and response pairs. So this is a formula that we can use for to get the reliability, how much we will get from each and every IC. So ideally it should be 100%. Yeah. What are the application where we can use this puff? Yeah. So mainly in IoT applications we can use this puff. So as you know, for IoT, for example, most of the uh, experiments we will use some Raspberry Pi application, Raspberry Pi devices to build any IoT systems. Okay, so here for this POF actually each and every IoT devices will include this POF. So it is a unique ID. So here we have two things. First one is enrollment, then verification. Okay, so in the process of enrollment, that main trusted company who is manufacturing these ICs as well as your POF. So they know the challenge and response pairs. So for this challenge, what is the response? For this challenge, what is the response? So that's for the enrollment process. The next one is verification. So verification, what you will do is, so after giving some challenge, you can see here R and C. The C meant for challenge, R meant for response. So for this challenge, what is the response? So it is going to verify by using some pre-recorded CRP. CRP means challenge response pairs. For each and every IoT device, this table will be stored in their trusted companies. Okay. So whenever you are going to use this IoT device, it has to authenticate. Okay. So suppose this IoT device is manufactured by the Atmel, for suppose, but using some IC overbuilding or IP piracy, the same device may be manufactured by some other companies. But whatever the devices will be manufactured by Atmel, so that is trusted one. Okay, but by doing reverse engineering, the same IP they might be used in the black market and they can fabricate some other different duplicate ICs. So that we can protect over here. Okay, so this IC already authenticated by the Atmel. Okay, so whenever you are giving some input to this IC, okay, so that is what the challenge input, and after giving the challenge, this POC will give one response. So this response will go to the untested environment. Again, the same response will go to the verification authority. So if this device is manufactured by the Atmel, then it will check for this challenge what is the response. It will check the table. So the same response it is giving from the IoT device or not. If it is not, if the both responses are not same, means your IoT device is false. Otherwise it is otherwise it is otherwise it is a false device. Okay, so in this way you can authenticate your each and every IoT device. Okay, so if you have the large number of CRPs, means it is good, because normally we have some, this is 4-bit challenge and response pairs. So if you have more challenge and response pairs, that will be better, and that is the strong point. If we have only less challenges, means like 2-bit, 3-bit, 4-bit, means 4-bit means only 16 combinations that you can build. So that's very easy to crack that even. Okay, so that's why we have to go for a higher number of bits. So here we have seen one of the application of this PUF we can use in not only IoT, any uh, authenticated device that you can authenticate by using this by using PUF implementation. And nowadays these PUFs are very common in most of the processors, okay, or uh, all the Intel processors and the Cortex and all these processors, they have this PUF. Okay. So here I'm going to tell you about one. Yeah, yeah. So this PUF is and in the literature we do have so many different kinds of PUFs we have. The basic example is this ring oscillator PUF. So like we have so many like arbitrary PUF and butterfly PUF. Okay, so many kinds of PUFs we have. But here, so in this slide, I'm going to explain one of my work here. So this is a chaotic logistic map. So here, what we did is, so we proposed one random number generator here. So as you know, chaos means it's just like confusion. You don't know whether what it is coming here. So here we are going to propose one hardware architecture for this chaotic logistic map, and the main thing is we are proposing this random number generator. This model we are going to uh, propose by using the chaotic as well as pop. So both things we have included in our proposed work. Okay. So a micro hardware architecture that is a chaos generator is recently reported, and you can use in so many communication systems like thwart or SPI. Okay. So these systems have more random behavior and unpredictability than other conventional PRNGs. Normally, random number generators are two types: pseudo random and true random. We do have yeah. So normally, random number generators are basically two types: pseudo random number generators, and the next one is true random number generators. So pseudo random number generators, these generators are vulnerable to attack because it is quite predictable. Normally, random number generator means you can't predict what the future number is it is coming. But pseudo random number generators are which are a little bit vulnerable. So you can expect the future the numbers. Okay, but coming to the true random number generators that you can't predict. Okay, it is more quite difficult to predict the numbers. So this uh, here we are using this puff. Okay, this is hardware related actually. So you can't predict exactly. So it comes under your true random number generator. So to avoid this chaotic logistic map, so it is a simple expression. So xn plus 1 is equal to xn into so 1 plus or xn, the condition one logistic map it is. So it is basically depends on the input conditions. Okay. So initially I will give some parameters and initial values. Then it keeps on giving some different values. So that's what the chaos. So this dependency, okay, suppose if I know that parameters, okay, and the input values, then I can easily predict what the feature number it is coming from your pseudo random number generator. So this we want to overcome that. So what we did is, so we have proposed one CPRNG So chaotic pseudo number generator, normally this is the expression just now I told you, xn plus 1 is equal to r into xn into 1 minus xn. So xn is the first initial value, x0, suppose n equal to 0, then x1 equal to r is your some parameters, control parameter. So that might be in the range of 0 0.2, 0 0.4. Okay, so during that range only it acts like a chaotic. So by giving the first initial value, then it keeps on giving some different values, just like a feedback thing. So here, so this is a circuit, this is a block diagram, and this is your logistic map equation. So what we did is, so the same thing, so the same logistic map we are implemented by using some registers. Okay, so this is a micro hardware architecture it is. So it is already published in IEEE Embedded Systems letter. So this is some the previous work. So what we did is, so this CPRNG means this logistic map. So we have added one more block called PUF. So it is basically RO based puff. Okay. So what we did is, so we interconnected with pseudo random number generator. So the challenge for the puff no challenge and response. So the challenge will be given by the random number generator to the puff, and the puff again it will give some response, and that response it is going to the CPRNG. Okay. Normally CPRNG means every time you need in CPRNG for initially you need to give one number, that's the initial values and some control parameters. Initially you have to give once, after that you need not to give. But here what we are doing is just we have changed the pattern. Okay. So every time the challenge will come from the random number generator, that will be given to one puff, and the puff response again that will be given to the CPRNG input. So it keeps on continuing, and we are getting that random number generator output as an random numbers. So we have two inputs. I just now said initial seed, initial value, and initial count. Okay. So this is the block diagram here. So here what we are using here is, after getting the CAMOUFLAGING output, suppose it is some 16-bit. Okay, in 16-bit, again the puff, some of the bits are going to the puff as a challenge, and the corresponding uh, challenge bits you will get one response. That response bits and this CAMOUFLAGING output, both I'm going to concatenate that. Then finally that concatenated output is like your random numbers. Again, some of the bits are going again input to your CAMOUFLAGING. So it keeps on doing that. So here this work is we publish in the IEEE transactions on the LSA. So here whatever the numbers you're generating, okay, so how you can say that that is a random number or not. So to clear that, what we did is we have taken some NIST results. This is the National Institute of Standards and Technology. So they have some suits. So it is a 800 22 test results. It is a random test suit. So if you give all the random numbers that you have generated, so as an input to this test suite, it will give you some test results. These are all statistical test results. So what is the frequency? What is the frequency within a block? And how many number of runs you are taking? And is there any longest run of ones are there, zeros are there? Even though some linear complexity, entropy, and random excursion. So all these statistical test runs will be executed in this test suite. Okay, after giving your random numbers all maybe 10 lakhs of your random numbers you have to input to this test suite, then it will give you this results. P value will be given. So based on this p value is more means your randomness will be more. Okay, probability values. So this is the way we can test whether our the random number generator is true random or not. Okay, this way we have to prove that. So these random numbers, we can use it as a keys, crypto algorithms, or during encryption. Okay. So everything there you can use this random number generator, which are very more powerful, and you can crack that the numbers. So here one of the example have which is ARM tester. You know, all everyone the ARM processors or controllers. So, so Cortex A9, AI, A15, and so on. So here, so each and every these processors, they have some trust chip. Okay. So what is this trust chip? So on your chip, on your processor or controller, some part is what trust chip. So what it means, it enables the specialized and hardware-based form of the system virtualization. And this trust zone provides normally two types of zones, like normal and trust zone or secure zone. So what will happen? Normal zone means it acts like a normal your processor or controller. But what happens with the trust zone is, so the multimedia operating system we are using so runs in the normal zone, and while the security critical software, okay, like some crypto or encryption things or decryption things, so these kind of blocks will be run in the portion of your trusted zone, so that no one hack the information or no one grab that information. Okay. So in this way, we are going to run that specialized or critical software or hardware things will be run on that zone. So it is a capability of inherent in modern ARM application processor cores, including all the recent Cortex A8, A9, and A15 cores. See here, you can see in this figure, this is ARM test zone. So in the normal zone, all the normal operating system, whatever Android or whatever the operating system that we are using in our system, and some secure critical software things. Okay, so that will be executed in your trust zone, and the transaction, you can see the security critical software that can access the normal zone, but the normal zone that operating system cannot access the trust zone. Okay. So in this way, we are going to secure our some critical software parts. So this chip manufacturer also, they permit some of the pod will be like a secure zone, partitioning of your memory, and or there were some input output peripherals will be some interrupts. Okay, in your SOC, whatever you're proposing, those things it is going to include in your trust show. And furthermore, some of the chip providers must open the secure zone for third-party trusted OS and applications. And this is for the ARM trust zone. This is one of the example. Yeah, here you can see. So this is a virtualization of your trust zone. So normal zone, you're executing one of the OS, either Windows or Linux. And coming to the trust zone, you can see here all the code things for the access control and the crypto suite, key management, okay, mValid. So all these critical software parts, they are going to execute in this trust zone only. Okay. So in this way, they are going to secure even your ICs and the software which is executing in your hardware image. Yeah, so these are the one of the practical example to secure your hardware ICs. So with this, I'm going to conclude this session. Dear participants, if you have any doubts, please ask the question. Yeah, I sent a feedback link. Please check it. Kindly fill the feedback link. And thank you, participants. So tomorrow we have the session in the morning at 10 a.m. By Dr. Subhashish Mahapatra is from VIT. The topic is IoT and robotics. So, in this, so by this I am going to conclude this session. So thank you everyone. Kindly fill the feedback form. Thank you.